Solar power feels like it's been around forever, but it's really only in the last couple of decades that it's truly taken off. Today, we're going to unpack the quantum mystery that actually stalled solar for 60 years, and then we'll look at the new breakthroughs that are now completely shattering its old limits. Okay, so let's just dive right into the central mystery here. The very first working solar cell? It was created by an inventor named Charles Fritz way back in 1883. But then, nothing. For more than half a century, progress just kind of stopped. So why would a technology with so much promise just sit on a shelf for that long? And this timeline really shows you the problem. Fritz's first cell had an efficiency of about 1%. Pretty terrible, right? Then, crickets. Until the 1940s, when researchers at the legendary Bell Labs created the first modern silicon cell, and its efficiency was 10 times higher. It's really from that point, in the 40s, that we start to see the steady march of improvement we all know today. So what was the reason for that 60-year gap? Well, it turns out Charles Fritz had stumbled upon a quantum engine, but he didn't have the instruction manual. He knew it worked, but he had absolutely no idea why it worked. It wasn't until we really understood the strange rules of quantum physics inside a material that we could finally pop the hood and start tuning this thing up. All right, so here's our first quantum ingredient, energy bands. Think about it like this. In our world, you can throw a baseball at any speed you want. But for an electron inside a crystal, that's just not true. Quantum physics says, nope, you can only have certain allowed energies, and we call those bands. And in between those bands are these band gaps, forbidden zones where an electron simply cannot exist. The second ingredient is something called the Pauli exclusion principle. And this is a hard, fast rule of the quantum world. It basically says that no two electrons can ever be in the exact same state at the same time. The analogy from the source material is perfect. It's like a school bus with assigned seats. Once a seat is taken, it's taken. Another electron has to find the next available open seat. And this is where those two rules create some magic. In a normal piece of metal, if an electron gets excited with extra energy, it loses it almost instantly. But in a semiconductor, those two rules create a kind of trap. The band gap means the electron can't just lose a little bit of energy. And the Pauli principle means all the lower energy seats are already taken. So the electron gets stuck, holding on to that energy for about 10,000 times longer than it would in a metal. And that tiny delay, well, that's the entire secret to making a solar cell work. Okay, so we've got this electron, and it's holding on to its energy for a relatively long time. But how do you actually harvest that energy? That's our third ingredient, the p-n junction. It's a clever bit of engineering where you create a permanent built-in electric field inside the semiconductor. This field acts like a slide, basically. It grabs those excited electrons and whisks them away to the metal contacts before they have a chance to waste their energy as heat. And that flow of electrons, that's your electricity. So once we finally understood that quantum engine, we could really start designing much better solar cells. Let's look at one of the biggest real-world innovations that has come out of this understanding. Panels that can literally see on both sides. They're called bifacial solar cells, or BSCs, and the concept is just beautifully simple. A traditional solar panel, it only makes power from the light that hits the front. But a bifacial cell is designed to generate electricity from light hitting either the front or the back surface. So how does that even work? Well, it's all about something called albedo, which is really just a fancy word for how much light a surface reflects. A bifacial panel doesn't just capture the direct sunlight from above. It also soaks up all the light that bounces off the ground or the roof below it. It's such a simple idea, but it gives you a pretty significant power boost. And the advantages are actually huge. First off, you get more power from the exact same amount of space. But you can also do really clever things, like install them vertically. Imagine a vertical fence of solar panels facing east and west. It generates a ton of power in the morning and evening, right when we need it most. This helps solve that infamous duck curve problem for the grid. It also opens up brand new possibilities for agrovoltaics, where you can grow crops between the rows of panels. They even stay cleaner in dusty places like deserts. And believe me, this isn't some niche product. Bifacial panels already made up 20% of the entire market back in 2020. And by 2030, that share is forecast to explode to 70%. This technology is very quickly becoming the new standard. But what if we want to go even further? Really push the boundaries? Well, the next great leap in solar is all about tackling a fundamental barrier, a hard limit that has defined the absolute maximum efficiency of solar cells for decades. That barrier is known as the Shockley-Queisser limit, and it's basically a hard ceiling from the laws of physics that says a standard silicon solar cell can never, ever be more than about 34% efficient. That's it. A huge chunk of the sun's energy just gets wasted as heat. For 60 years, we've just been creeping closer and closer to that limit, but to actually go beyond it, we need a totally new design. So, enter the tandem cell. Now, the traditional way to do this, on the left, is called a series tandem. You just stack two different solar cells on top of each other. It works, but it's got a huge problem. The electrical current flowing through both cells must be perfectly identical, and that's super hard to do when the sunlight changes. The new idea, on the right, is a parallel tandem. Here, the cells are connected side by side, and instead of matching their current, they only need to match their voltage, which is way, way easier to do. So, how do you match that voltage? Well, this is where a truly mind-bending quantum process called singlet fission comes in. With certain special materials, when a single high-energy photon from the sun comes in and hits it, it creates an excited state that almost instantly splits into two separate, lower-energy excited states. It's like getting two for the price of one. One photon of light goes in, and you get two potential electrons of current out. This doubles your current, which perfectly halves your voltage, letting you match it with a standard silicon cell. And this chart just shows you exactly why that matters in the real world. This is the theoretical efficiency over a whole year in the cloudy Netherlands. The regular cell is stable, but, it's limited. The traditional series tandem in blue, it's all over the place. Its efficiency just tanks when the sunlight isn't perfect. But look at that green line. The parallel tandem is rock solid. It maintains its huge efficiency advantage day in and day out, rain or shine. So what's the bottom line here? Over the course of a full year, a series tandem might give you 18% more power than a standard cell, which is good. But the parallel tandem, because it's so stable, could generate 33% more power. That's not just good, that's a game changer. But here is where it gets truly wild. In a 2016 experiment that was proving this parallel tandem concept, researchers measured this number, 106%. Now hold on, that is not 106% overall efficiency. We haven't broken the laws of thermodynamics. This is something called the external quantum efficiency. It's a simple count. For every one photon of light that goes in, how many electrons of current do you get out? And for the very first time, the answer was more than one. This is the smoking gun. It's definitive proof that this 2-for-1 quantum trick actually works. So this isn't just some weird thing you see in a lab. It's a blueprint for a next-generation solar cell that's not only more efficient when the sun is perfect, but it's fundamentally more robust and productive in the real world, where clouds happen and the sun isn't always shining perfectly. And that really leaves us with a fascinating final thought. We've just seen a technology that uses a bizarre quantum trick to get more than one electron of current from a single photon of light. It breaks a barrier that for a long, long time seemed absolute. And it really makes you wonder, what other fundamental limits in energy are just sitting there, waiting for the right clever idea to come along and break them?